We started with bivariate random variable and joint probability function. Associated with that, there is one topic which is called correlation, which is very important, and it is from module 4. So correlation, I want to cover first, and then I'll go back to the topic of unit 3. So my today's topic is correlation, and the mathematical tool which is used to measure correlation is called the product movement correlation coefficient, as you can see written in the heading, or Carl Pearson's correlation coefficient. Carl Pearson is the statistician who developed the tool for studying correlation. Let us try to find out the meaning of the correlation coefficient first of all. Let us look at the definition first of all, and then I'm going to tell you about the meaning of the correlation coefficient. So as it is given in the, as it is written in the note, let us read it together. We consider a paired data set which is written as XY, capital X and capital Y, representing bivariate distribution. We can calculate the association between the two variables. The association between the two variables here is quantifiable. The measure of association is product movement correlation coefficient, or Carl Pearson's correlation coefficient. What do we mean by the association between the two variables? That is a very important thing. You have to understand this part pretty clearly. Now, say for example, if we wish, we can associate two different things. These things may be dissimilar things, but we can associate. You can try to associate them. We can try to associate these items. Say for example, if I consider a random variable capital X to be the student's mark in a certain examination, and suppose capital Y is the student's mark in certain examination, and capital X is price of petrol, the hike in the petrol price during the last year. Suppose I am considering the association in this manner. Here also, we are considering two different random variables, capital X and capital Y. Capital X gives you the price of petrol, and capital Y is the mark of the student in a certain examination. Apparently, it looks there is no association between them, because there is no relation. There shouldn't be any relation between the hike in petrol price and students' performance in a certain examination. So when we try to associate two different things, two different random variables, that association must be a meaningful association. It is not just an arbitrary association. Now, suppose many students are saying, suppose somehow I have got some sets of data for the petrol price and an equal number of data for the marks of students. Okay. Suppose on a particular day, the student is sitting for an examination. I'm looking at his performance, and on another day, the student is on that particular day, what was the petrol price over there? Now, an equal number of data for petrol price and marks of students are available with me. With the help of the Carl Pearson's correlation coefficient, I'm able to somehow calculate the correlation coefficient between these two items. Now, apparently it looks that there is no association between the two, and probably it is right. But if one person claims that, okay, since there was a hike in petrol price, student and at the same time there was a kind of strike in railways, the students had to cover a long distance from his home to the examination center, and due to the hike in petrol price, he couldn't avail uh, cabs. So he went for break journeys. He several times he changed his mode of traveling. Like first of all, he used bus, and then he used for certain distance he used cab, and then again he used some. He had to shell out money for rickshaw, whatever. Several mode of transportation he has used to reach to the examination center, and therefore he became extremely tired, and therefore his performance was poor. Somehow the person is able to find out some sort of association between the two. Now we have to think whether indeed these things, this tiredness of the student is affecting his performance or not. Okay, so association, if you give a little bit of I mean effort in your thinking, then you can find a little bit of association between any two items, I think. But not every association is correlation. Okay, for this, the example which I have just now told you is an example of causation. It is called causation. The student's tiredness due to traveling is causing this, affecting his performance in the examination. It is not correlation. It always doesn't happen. Sometimes it happens for some students. So it's a, if the values are given, capital X and capital Y, with this, with which one of which is giving you the price in petrol, and another giving you the marks of student, then that will not be an appropriate example of correlation. Correlation must be free from any causation effect. So correlation and causation, these two things are not different, not same, they're different. Now let us come to the correlation factor. What is correlation? Very frankly speaking, correlation between two random variables is that entity which gives you some sort of relation between the two variables, and it always happens. It is not that sometimes it happens and sometimes it is not. Such two variables, if you can identify any, they are having this sort of correlation always between them. Say, for example, I can cite an example of a pair of random variable where one particular variable representing price of item and another particular variable representing demand of item. And you always know, and it has been happening ever since due to the nature of the human behavior, that whenever price increases, demand decreases. Irrespective of in which particular era you are living, it is always true for any human being. Another example you can cite, that income and expenditure. When income of the person increases, the expenditure of the person also increases. Previously, when your income was poor, you used to buy your groceries from your nearby grocery shop. And now, since your income has increased, you want to go to Spencer to buy items. Okay, so this sort of items, this sort of pair of variables, we can very well say that it is irrespective of the era in which you are living. These things are always having kind of association between them, and this is not a kind of causation. It is not a causation effect. It's called correlation effect. And how much correlated these types of variables are having between them, that quantification can be done by using a formula which is given by Karl Pearson, and it's called Karl Pearson's correlation coefficient, or sometimes it is called product moment correlation coefficient. Okay, one thing you have to remember, that whenever you are taking capital X and capital Y, two variable, the number of items present under these two variables must be equal. It should not be that capital X is having 8 values and capital Y is having 10 values. Then you will not be able to find the correlation coefficient. So I'm noting this point over here. It is a very important point. You somewhere do write in your copy that to calculate correlation, between capital X and capital Y, number of elements in X and Y must be same. Remember this, it is a very important point. Okay. So let us now try to find out what is the formula for calculating the correlation coefficient. Okay. Let me scroll down a little bit. This is the formula for calculating the correlation coefficient. Okay, the correlation coefficient is denoted by Rxy. There are two notations for calculating the correlation coefficient. One notation is you can write R, and in the suffix you can write capital X, capital Y. It's not a product which I have written over here. It is not X into Y. It is not X intersection Y. It is not X comma Y. We will read it as just XY. Or you can do one thing, you can write R, and inside the bracket you can write X comma Y. This is the notation. And this is the computational formula for calculating correlation. Just look at the formula. Probably you are thinking that this formula is too complicated. Okay, so how can we recall that? There is a very easy way to recall this particular formula. You don't have to recall this in this manner as it is written in the note. You can write the formula of correlation as this. Correlation is defined by the ratio covariance of XY. It is called covariance of XY. You are already familiar with, by sigma X into sigma Y. Now look at this formula. Try to correlate the numerator and denominator here in these two cases. The numerator is representing the covariance between the two variables X and Y, and you know the formula is given by this, and the denominator is given by this. Root over summation I goes from 1 to n xi minus x bar whole square, and root over summation I goes from 1 to n yi minus y bar whole square, because sigma, this is the standard deviation and that is the standard deviation. Actually, this is the formula. This is the formula. Now you can see that in the numerator we have 1 by n, and in the denominator we have 1 by root of under square root 1 by n twice. So 1 by root over n whole square means 1 by n, and that 2 1 by n will cancel each other. Okay, so that's why it is written in the following manner. So this is the formula, computational formula between of the correlation coefficient between the two random variables. Okay. Another computational formula is there, which you can use sometimes, and you can say that, for example, the actual formula for the correlation coefficient, the actual formula for covariance is this, as you can say, 1 by n summation xi minus x bar into yi minus y bar. Now what you can do is that you can take the product of these two items, two factors, and you can operate the summation on each of these items. Let's see what is happening over here. So I am taking the product. So xi minus yi, xi into yi minus xi into y bar minus x bar into yi plus x bar into y bar. Now I'm writing 1 by n summation xi yi minus 1 by n summation xi y bar minus 1 by n summation x bar yi plus 1 by n summation x bar y bar. Now 1 by n summation xi yi will remain same. So I'm writing it in this manner, and you know y bar is constant, so we can take this y bar outside the summation sign. So I'm writing in this manner, y bar into 1 by n summation xi. Here x bar is the constant quantity. So we can take x bar outside the summation sign. And here x bar, y bar, both of them are constant. So we can take them outside the summation sign. And inside 1 will be there only. Okay, I hope you are actually following me. And now you see, I'm writing over here that I'm not changing the quantity 1 by n summation xi yi. It will remain as it is. But 1 by n summation xi is x bar. So we can write it as x bar into y bar. 1 by n summation yi is y bar. So again, we can write it as x bar y bar. And 1 by n summation 1. Summation 1 means summation I goes from 1 to n 1. That means 1 is added with itself n times. So that is equal to n. So 1 by n and n will cancel each other and we'll get plus x bar y bar. So 1 x bar y bar, 1 x bar y bar will cancel each other and we will ultimately get 1 by n summation xi yi minus x bar y bar. So you see, that's how we have got the numerator part. Similarly, if you take the formula of sigma x square, which is the variance, which is xi minus x bar whole square, 1 by n summation xi minus x bar whole square, you can very well show that it is by breaking the square, you can show that it is exactly equal to this. And similarly, you can also show that 1 by n summation yi minus y bar whole square is similar to 1 by n summation yi square minus y bar square. So you can easily derive. I'm leaving these two items for you to derive by yourself. Okay. So you can use this formula to calculate the correlation coefficient, or you can use this formula to calculate the correlation coefficient. Okay. So that is how we calculate the correlation between the two random variables, with the help of Karl-Pearson's correlation coefficient formula. Okay, I'll recommend both of these formula, and I'll ask you to remember both of these expressions. Okay, this will help you to generate either of these two formula. This is the actual formula, covariance xy by sigma x into sigma y. Okay, so let's proceed. I hope that you have copied it already. So, and you have to be pretty fast in copying, because otherwise it will kill our time. If you're not able to copy it quickly, then you can take the screenshot. That will be all right also. Okay. So let's see what is there next for us. Okay, another formula, another form of correlation coefficient formula is given by this. Just look at the formula. This is, you already know. This is actually coming from the definition. But between these two, there is another formula which is written in terms of expectation. Because if you can recall that the covariance of xy can also be written in the following manner: E of expectation of x minus ex into 1 y minus ey. Why it is so? Because you can think E to be an operator which is standing for 1 by n summation. And you know that E of x is equal to the mean x bar. So now let us try to replace this. So what we will get? We will get this one. Now you see, it is our familiar expression which I wrote over here. So and similar is the case, and you know very well that this expression under the square root is called the Vx. We have several times discussed it. So in terms of expectation and variance also, you can represent the correlation. You can also represent the correlation. Okay. Understood? So this is another expression which you can use. This is another expression that you can use to calculate the correlation coefficient. Okay. Now I'm going to show you a very simple calculation with the help of Microsoft Excel, which you can use to find the correlation coefficient between the two variables. And I'm going to show you how to calculate the correlation coefficient using your Excel, because sometimes you have to deal with a large amount of data, and the manual calculation is not going to help you in this regard. So you have to know how to deal with that amount of data with the help of Microsoft Excel. So I'm going to talk about that right now. Okay, so let's begin. I hope you are able to see the Excel file, and in Excel file you can see that I have used I have considered two variables, capital X and capital Y over here, and capital X is having 5 items with some values 1, 2, 5, 6, 7, and capital Y is having 5 items. The values are given to be 3, 4, -1, -6, and 10. Now only 5 items are present over here. Now, can you say what can be the correlation coefficient between these two? Will you tell me that whether capital X is increasing? Both of them are in increasing direction, or both of them are in decreasing direction? Can anyone say this? How capital Y is associated with capital X? Okay. First of all, whenever you get the correlation, whenever you get such a bivariate data, just do not attempt to calculate the correlation coefficient between them. Your first requirement is to plot the data. Your first requirement is to plot the data and try to see how the data is being visualized. I mean, how one particular data is being if you plot the two items, capital X and capital Y, then what is the nature of the plot? That you have to first identify. Okay, after that, you can go and attempt to calculate the correlation coefficient between the two. To do this, what we do is that we select the chart in this manner. Then we go to the insert section. In the insert section, you can find that there is a plot which is called scatter. Let us try to read what this particular icon is saying to us. Scatter plot, this icon, it helps us to insert a scatter chart, also known as an XY chart. Okay, and this type of chart compares pairs of values. Also, it is written, use it when the values being charted are not in x-axis order or when they represent separate measurements. So I am going to select this scatter plot, and from this, I'm going to select this one. Now try to look at this. See, this is my scatter plot of the following sets of data. This is how they are associated. For this value of X, capital Y is this. For this value, capital Y has further increased. Then suddenly at 5, capital Y has decreased. For 6, capital Y has further decreased. And for 7, it suddenly jumps. So that is how the that is what is being represented by the plot of capital X and capital Y. And this plot is not telling us what sort of association are being played between the two variables, capital X and capital Y. So the only way out, because sometimes it is increasing and sometimes it is decreasing. So we do not know what sort of correlation is actually affecting them. So what you can do here is you try to calculate the correlation coefficient between the two, and then you try to find out what sort of association are actually being carried forward by the two variables. To find the correlation coefficient, what you will do is that you will select any arbitrary cell, like I'm selecting this cell B10. Now you go to this section, formula section. In the formula section, you have this option, as you can see, more functions. So you click on that. Under more functions, you have this option which is called statistical. And inside that, you try to find out the key which goes by the name correl. Correl, as you can see, it is saying that it returns the correlation coefficient between the two sets. Click on it. Array 1 stands for the sets of values which are given under the banner capital X. Array 2 is the set of values which are given under the banner of capital Y. So let us try to select array 1 first. So we'll do it in this manner. And let us try to select array 2, which can be selected in the following manner. So array 1 goes from A3 to A7. Array 2 goes from B3 to B7. And you are already able to see the value, which is minus 0.0324, like this. Click on it, and that value is printed over here. That value is printed over here. So my point is, when correlation coefficient between two random variable is negative or less than 0, then X and Y are negatively correlated. Negatively correlated. That means if one variable is increasing, another variable is decreasing. Wherever the amount, the quantification, if you quantify, this amount of decrease is very poor, very low. In some cases, it has increased. In this particular case, it has increased, but here, in these two cases, it has decreased and suddenly it jumps. But still, as the measurement is saying, is telling us, although the amount of correlation is poor, very low, but it is negative, and therefore the direction of the two variable is opposite to one another. When Rxy is positive or greater than 0, then X and Y are positively correlated. By positive correlation, we mean either both of them are increasing or both of them are decreasing. That is called correlation, positive correlation. And when Rxy is equal to 0, XY, this implies XY are not correlated. These three important points are you are supposed to remember. I will talk about this part later on, because you have to understand something about this part. This is not so easy, as you can see. This particular portion that Rxy equal to 0 implies X and Y are not correlated actually is a kind of thing like when we say phi is null set is a subset of any set. That particular sentence is also very confusing. This sentence is also very confusing. I have to give a significant amount of time to make you understand what does that mean actually. For the time being, you are having this. What I will do now, I will change these values a little bit and let us try to find out how the scatter plots changes and what the value of the correlation coefficient becomes. So, okay, let us take this to be 7, this to be 8, and that to be 9. Now you see, the correlation coefficient here is positive, and it is what? Exactly, it has become 1. Just note it down. So my point is that when Rxy is equal to 1, X and Y are having perfect positive correlation. X and Y are having perfect positive correlation. Okay. And I'll change the value a little bit further over here. And let's see what is happening over here. Just you just note down these values which I've taken into consideration. This is another example where I have considered 1 and 3, 2 and 4, 5 and 7, 6 and 8, 7 and 9. What I have done over here, actually I have added 2 to the value of X. So 1 plus 2 is 3, 2 plus 2 is 4, 5 plus 2 is 7, 6 plus 2 is 8, and 7 plus 2 is 9. Actually, here you can, if you observe that the variables capital X and capital Y are actually having some sort of relation, linear relation among them, which is given by Y equal to X plus 2. Okay. So a kind of linear relation is playing over here. Let us change these values further. Okay. So now I'll consider this. I'll consider that. See, this is also a kind of positive correlation you are getting over here. But you can see both the values. My previous example, I mean this one, this example was of this kind. Both of them were increasing. This one is an example where both of them were decreasing. But still the correlation between them is positive. Here X, Y, X is 1 and Y is -3, 2, 5, 6, 7. Now this is increasing, but that is also kind of was maintaining the linearity between the two. The linear nature of this and linear nature of this are actually same. So therefore correlation coefficient came out to be 1. Okay. So therefore the tendency of the curve is like this. This is the tendency of the curve. The linear nature of the two variables are similar in this particular case. And therefore the correlation coefficient is coming out to be 1. Now my time is running out. What I wanted to show is that by a similar example that if Rxy is -1, X and Y will have negative, perfect negative correlation between them. In the next session, I will try to show this to you. I hope all of you have written your roll numbers in the chat box. Okay, so I'm concluding my session at this point. Let us meet in the next session.